Okay, number 7 on the fall 2011 exam 4 has a solid cylinder rolling down a 20-degree incline without slipping, and we want to determine the linear acceleration of the cylinder. When we worked this problem in lecture, we did it using F equals ma. We want to determine the acceleration. We have to factor in the rotation as well as the translation. So let's draw F equals ma, free body diagram, kinetic diagram. Let's use x along the incline, y perpendicular to it. Okay, the forces on the cylinder are obviously the weight. Okay, the friction is going to be up the incline, and we'll have a normal force. Okay, as far as accelerations go, we're going to have a linear acceleration and an angular acceleration that we have to consider. Okay, we're going to need I for a cylinder. We have to look that up. For a solid cylinder, it's 1/2 mr squared. And we also are going to need to relate alpha and a sub x. So we know a sub x is equal to alpha times the radius. Okay. We're going to look at the center of the cylinder. Okay. And we're going to write 3 equations. We're going to write torque equals I alpha. We're going to write the forces in x equals mass times acceleration in the x, and forces in y, mass times acceleration in the y. Okay. We have to be really careful with our torque equation that we're consistent with the direction. Okay. What's causing the torque? If we look at the center of the object, we have the normal force going through the center, we have the weight going through the center. So the torque in this case is going to be caused by the friction and the distance of the radius. Okay, that's going to be in the clockwise direction, and we've drawn intuitively, we know that it's going to be rotating as it goes down in the clockwise direction. Okay, so those two things will need to be in the same direction. If we do as we normally do and use counterclockwise as positive, so I'll draw that up here with my coordinate system to remind myself that counterclockwise is positive, this equation will become minus F times R because it's a clockwise rotation, and my I alpha is going to be negative based on how I've drawn it. Okay. So a little tricky to keep track of the signs. You just if you step back and look at it, you can hopefully see that those do need to be in the same direction. So you don't want to put negative on one and positive on the other. Alright, so that's going to be one of our equations we'll use. In the x direction, we're going to have minus F, which is our friction force, and then we're going to have a positive W sine of 20. Okay, we'll go ahead and draw that out just for those of you. The weight is going to be broken into those two components, and there's my 20 degrees. Alright, so this x component of the weight is going to be the total weight times the sine of 20. Okay. So in the x we have the negative friction force and then positive component of the weight, and that's going to be the mass times acceleration in the x. Just for completeness, I'll write the y equation. Turns out we won't need it, but it would be n minus w cosine 20 equals 0. Okay. If we look at these two equations right here, the torque equation and the x forces in the x equation, they both have a friction in it that we can eliminate by solving for it in one and substituting in the other. They have acceleration and alpha, so we can relate those as we did up here. And we have an equation for I. So these two will hopefully give us an equation for acceleration in x. So I'm going to use this one first. It doesn't really matter which one we do first. Let's go ahead and solve this one for f. Okay, so f is going to be I alpha over r. Okay, I we said was 1/2 mr squared. Alpha, okay, right here we can write alpha equals a sub x over r. And we can, so there's my I, there's my alpha, and I have an r over here. So it turns out the friction force, looks like the r's will cancel. It's just going to be 1/2 mass times acceleration in x. Okay, that's the friction force it would take to roll without slipping. So now I'm going to plug that back in to my equation right here, and that's going to give me minus 1/2 max plus mg is my weight, sine of 20 is equal to max. Okay, we're getting there. Looks like I have mass in every term, so that will cancel out. Okay, and I'm just left with, switch back to my colors, so I take this 1/2 ax over the other side. Okay, I'll do it in two steps here, so I'll have g sine 20 is equal to 3/2 a sub x, or a sub x equals 2/3 g sine 20. And then finally plugging in some numbers, 2/3, 9.81, sine 20, and that number will come out to be 2 divided by 3 times 9.81 times sine 20, 2.24. meters per second squared. Okay, if you use g as feet per second squared, that's 32.2 feet per second squared, that's fine. We didn't specify units. That answer would be 7.34 feet per second squared. But it's important to get the concept of what's happening here. We're factoring in both the rotation and the translation accelerations. So we had to be real careful with signs, work through the algebra. A lot of things canceled out. Another way of doing this problem would be to use conservation of energy. Okay, conservation of energy, we could set initial potential energies final is equal to the final kinetic energy. Okay, we could relate the height and the distance traveled, and we can then find a final velocity. Then we can use a constant acceleration equation to get the acceleration that would give us that final velocity. Okay, that's posted on the website. I won't work through it here. This is the way we work through it in lecture. That's it.